What kind of discoveries lie ahead for the James Webb Space Telescope? Will it be able to detect alien life? How does it compare to Hubble? Let's find out.
3, 2, 1.
Welcome to Your Space Journey, where we venture into the future of space exploration. Your journey begins now.
Thanks for joining me today for Your Space Journey. Today we'll dive deep into the James Webb Space Telescope with Lee Feinberg. Lee has been the Optical Telescope Element Manager for the James Webb Space Telescope at the NASA Goddard Space Flight Center for the past 20 years. Lee led the telescope technology development and led the telescope from architecture trades and design activities to manufacturing through integration and testing. He was also a member of the optics team that determined the optical prescription to correct the Hubble Space Telescope and performed independent testing of the mirrors that corrected Hubble. The James Webb Space Telescope is an orbiting infrared observatory that will complement and extend the discoveries of the Hubble Space Telescope with longer wavelength coverage and greatly improved sensitivity. The longer wavelengths enable Webb to look much closer to the beginning of time and to hunt for the unobserved formation of the first galaxies, as well as to look inside dust clouds where stars and planetary systems are forming today.
Your Space Journey.
Lee, thank you so much for joining me. Really appreciate it.
No problem. I'm excited to be here.
Well, this is an exciting time for you. I mean, you and your team are starting to experience the fruits of your labor, years and years of hard work as the James Webb Space Telescope kind of begins its final adjustments to begin its science mission. How are you feeling about that?
I feel really great, actually. It's we've waited a long time, like you said, and one of the reasons some of us have stayed on this long is because we wanted to be here when this happened. So it's very exciting.
That is exciting. Now, I do want to take a step back too, because you've certainly had an amazing career in the space telescope field, not only with James Webb, but also the Hubble Space Telescope. I wondered if you could tell us kind of how did your interest in space and or optics begin?
So it really starts with optics for me. I was interested in optics when I really was in, like middle school and high school, for two reasons. One is I'm legally blind in my left eye. So I was always sort of playing with my eye and trying to figure out, what was going on there. So I was a little bit interested in that. And then also when I was in high school, Star Wars came out and got interested in lasers. And I was like, I would like to build a laser. So I wound up going, even my undergraduate was a degree in optics from the University of Rochester. And I also was really into music, and the Eastman School of Music's there. So I was like, perfect fit.
Yeah.
While I was there, I actually worked at a laser fusion laboratory doing testing of optics, that were used in the laser fusion facility. So I was doing interferometry. And so that was like a great background that set me up for my NASA career. But it was while I was a student. Yeah.
Wow. That is amazing. I still remember when Star Wars came out, going to my high school teacher and said, I want to build a laser. And he kind of looked at me like, you're nuts. But,
Well, actually, mine did too. And I asked if I could build one as a research project. And they said, you might want to do that in college. So that's what I did. I waited till I got to college, and then I worked on laser.
And look at you now. I think that's amazing.
Yeah.
Now, and tell us about, I know you've had this amazing NASA career, but I do want to go in. So how did you become involved with the James Webb Space Telescope? And if you can tell us your role there as well, that would help.
Okay. So I'm the telescope manager. I've been that for 20 years. Mm-hmm. I had worked for about 10 years on Hubble, and actually got hired to work on the first repair mission for Hubble. And they call it SM1, Servicing Mission 1. Mm-hmm. I was about the youngest person on the SM1. I actually tested some of the corrective optics, the co-star mirrors, if you will, that were used to correct Hubble. Went out to the vendor and did my own interferometry. So I took that background from, undergraduate, and worked on my graduate degree while I was doing all this. And then, started working on instruments. I did a whole bunch of instruments on Hubble. I was the instrument manager for Space Telescope Imaging Spectrograph.
Nice. And
helped start the Wide Field Camera 3 and the Cosmic Origin Spectrograph. And then left Hubble for a couple of years and did technology development, all sorts of things, including large optical systems like interferometers and possibly segmented telescopes. Mm-hmm. But then I left NASA for a year And I went to a startup company that was doing a lot of undersea fiber optics and a lot of work with optical switching, which was part of my technology interest. But while I was there, 9/11 happened.
Oh.
And that was the point at which I realized the startup, was probably going to have a lot of trouble, and maybe I'd be better. And honestly, it wasn't quite as interesting as working for NASA. So I said, you know what, maybe I'll go back to NASA. So I called Bernie Seary, who was the very first project manager for what was then called the Next Generation Space Telescope.
Mm-hmm.
And I said, I'm thinking of coming back to NASA. Would you have a job for me? And he said, well, and I was expecting him, by the way, to say, yeah, you should work on the instruments, because I had done all these optical instruments for Hubble, and that was my background, and had a lot of that kind of background. And he says to me, I got a job for you. I want you to be the telescope manager. And I was like, well, I've never built a space telescope. And he says, nobody's built a space telescope like this before. Don't worry about it. So that's how it started. And that was, 9/11 was in September 2001. Mm-hmm. And I started a few months later on what was then called Next Generation Space Telescope. At that point, we didn't even know which companies were going to be building it. We didn't know what the mirrors were going to be made of. We didn't know we didn't know for sure what the segmentation would look like. And there was all sorts of things we just didn't know. And from that point to now, here we are aligning the telescope. It's been about 20 years of just work like crazy, make sure everything works, and here we are.
Well, it is amazing. And what I think is totally fascinating is how you did work with the experience of Hubble. And I do remember when Hubble was launched, I was, so excited about that. And then we found out the alignment was off, and it was so distressing. But then it was downright heroic to see NASA come together with a team like you and all the other people involved and be able to correct it. And just the views are tremendous. So to me, that gives me great satisfaction, because with you part of this team, obviously you've got great people working for you too. But it's like lessons learned from Hubble applied to the James Webb Space Telescope.
Yeah, and right? I even gave talks that were, applying lessons, Hubble lessons learned in terms of, how we tested things and all. So absolutely, there was a real continuity there. Mm-hmm. And one of the interesting things is, so after SM1, the data came down, and you may remember it made quite a big splash that, I think it was Barbara Mikulski, was the senator of Maryland, said, the trouble with Hubble's over, or something like that. And everybody was so excited. And I still remember when those first science images came down after we repaired Hubble, and how exciting it was. Yeah. And that's one of the things here on the James Webb Space Telescope that has really, convinced me to stick around to the very end. And I told that to a lot of other people on the project. I'm like, you have to stay for the end. There's nothing more exciting than working on something that you put in space that is doing total exploration, and then all of a sudden these images come down of things we've never seen before, and we're so close to that. We're within a few months of that, so it's really exciting.
And I can't wait. And for those of, I hope there aren't any audience members out there like this, but there could be some that are literally in a black hole, and maybe they haven't heard about all the specs of the James Webb Space Telescope. Can you just give us a general overview for it, as far as the mirrors, where it's located, and the size in general?
Yeah. Well, first of all, let me just say, why did we build it? I mean, it actually directly derived from fixing Hubble, because after we fixed Hubble, one of the things Hubble did is it did this thing called the Hubble Deep Field, and it looked at this very dark patch of sky at these very early galaxies. And but it couldn't go all the way back to the very first stars and galaxies. It went back to maybe when the universe was like 1 billion years old. Mm-hmm. But the light from the very early universe has been stretched into the infrared. It starts out as visible light, like the sunlight, but the universe itself has expanded. Space-time, the fabric of space-time has expanded, and as it does, it stretches the wavelengths of light into the infrared. So astronomers looking at this said, hey, we need a telescope that works in the infrared, longer wavelengths than Hubble can see. It needs to be huge, because we need enough sensitivity to see these very first, galaxies and stars. Mm-hmm. And so that's what set the spec. So the Webb is a 6.5 meter diameter telescope that, versus say 2.4 meter for Hubble. And because it's infrared, that means its mirrors have to be super cold. If they're not cold, and this is the problem with using Hubble in the infrared, the mirrors themselves will generate infrared light in the form of heat, and that contaminates your images. So you have to cool the mirrors to about minus 400 degrees Fahrenheit. And we do that by a couple things. One thing is we put up this huge sun shield. It's 5 layers. It's about the size of a tennis court. And each layer gets progressively cooler and cooler. And the inner layer kind of faces the telescope, which we allow to cool. And that telescope is facing deep space, which is super cold. And then what we do is we sent the Webb telescope all the way to the L2 Lagrange point, which is like 3 times past the distance of the moon, and is so far away that when we put up the sun shield, we can keep the sun, earth, and moon on one side and only be looking out at deep space. And we actually cool the telescope just by letting it cool off radiatively. It's a lot like putting up a parasol, on a sunny day and just letting it cool you off. And so that's sort of what we've been doing. We've been cooling since we launched this thing, December 25th, and we're still not at the cold temperature, if you can believe that. But we're getting there, and we're actually cold enough now that our infrared detectors work and our mirrors are working. So we got our first light, just our first photons, we call it, a little over a week ago, and we were able to find the 18 mirrors. So the first thing we do is we looked at a bright isolated star where there's no other stars in the field, just one. And each of the primary mirror segments, there's 18 of these hexagonal shaped mirrors that are the primary mirror segments, and each one's like 1.3 meters in diameter. But because they had to deploy, I mean, literally there are wings that deploy 3 mirrors each, and then the mirrors themselves have to move forward about a half an inch. So these mirrors are pointing in slightly different directions. They're not acting as a single telescope yet. They're actually acting as 18 separate telescopes. So the first thing we were doing was looking for this one star 18 times, and we expected them to be blurry because things aren't focused yet, they're not aligned yet, and it's exactly what we found. And we just released that last week, and that starts a process of telescope alignment where we then focus these individual mirrors, we make nice spots, we overlap the 18 spots in a process we call image stacking, and then we start the process of getting those different mirrors lined up as though they're a single monolithic mirror to a fraction of a wavelength of light. We call that phasing. And I describe phasing as, imagine you have a bunch of surfers, on different waves. When you phase something, they all need to be on the same wave. That's called coarse phasing. Get them all on the same. So imagine all these surfers, they're now surfing on the same wave. And then fine phasing is when they're not only on the same wave, but they're all on the peak of the wave together. And that's what we need to about a fraction of a wavelength of light. And when that happens, when those mirrors are all phased like that, a star, one single star, will look like one single star. And that's our goal. And we should be at that, in about a month and a half. And that's when we'll know we've built the right telescope.
See, and that's amazing. I was thinking about that. I saw those amazing first light images, and I believe the star is HD 84406. What fascinated me about that is the star itself is too faint for us to see with our naked eye from Earth. But once James Webb gets all the mirrors aligned, it's actually going to be too bright of a star. That's incredible. Yes.
It's actually already a little too bright of a star. So we moved on to some, not so bright, but we started with a star that you could actually see with binoculars. So it's not quite something you could see with your visible eye, but it's still a pretty darn bright star that's well isolated. There's no other star near it in our field, in the size of our camera, that's within a factor of 100 in brightness. Right. So it's very isolated. But yeah, I mean, we wanted a really bright star initially because we just wanted it to stand out relative to everything else. But as we go along, what winds up happening is if the stars are too bright, they saturate your detectors, and then basically you don't see anything, you just see like a bright spot everywhere. And so yeah, we've already sort of moved on. Yeah. So and Webb is going to be, this is the thing about Webb, is when it's fully aligned and built, it is going to be such a huge leap in so many fields of astrophysics and astronomy. It's not just this early universe, which is what it was designed for, but as an example, as we were building Webb, people realized that there are these exoplanets out there with atmospheres, and you can do a process by which, as the planets pass in front of stars, and normally there'll be a little dip in light, because you can imagine this planet, passes in front of a star, and the starlight dips a little bit as the planet passes in front. And that's how they find these planets. But in our case, we're going to take what's called spectra. We're going to separate the different wavelengths of light, and we're going to be able to tell the chemical composition of these exoplanets. Incredible. And we're going to do it on systems like the TRAPPIST system, which has 3 habitable zone planets. There's so much we could learn just about exoplanets, let alone the planets in our, solar system, as well as, galaxies and star formation. I mean, in nearly every area of astronomy and astrophysics. And in some areas, Webb is predicted to be 100 times more powerful in the mid-infrared, which we have this one instrument that's extremely powerful in the mid-infrared. Webb is about 1,000 times more sensitive than it's any previous mission that's been done. So we're talking 1,000 times. That's a big factor,
Yeah, it is. And Lee, what amazes me too is I know it's an infrared telescope, which is amazing. And I'm harkening back to the days when I was in astrophotography, in which I actually tried to use infrared film to take pictures, and we had to, really watch our gloves and everything just to even do that. But what is amazing too is I've heard that you also be able to process those images to convert them to visible light equivalents. Is that?
Yeah, exactly. I mean, if you think about it, your eye sees, the Roy G. Biv, right? Right. Because that's your eye is designed to do that. But imagine you had an eye that could do the same thing, but in the infrared, it would just see colors that way, right? It just happens to be we evolved that way. And why did we evolve that way? Because sunlight, it peaks at those spectrums. So the over many years, things evolved that way. But it's, it's basically a color spectrum, and we'll get a color spectrum in the infrared that we can convert to colors and make color images that are very similar to the color images your eye actually sees, but they're infrared images. And so, you're going to see, I think you will see color images somewhat like you've seen from Hubble, but with factors of 100 and 1,000 times more powerful than we've seen over a very large wavelength band. So even everything I've talked about is just a glimpse of the number of different areas of science. And in nearly everywhere we point Webb that first year, it will be like a new exploration. It almost would justify a whole mission in and of itself, each one of these things. We actually know, because astronomers had to propose to use it. There were certain proposals that were selected. There's a list, they call them cycle 1, and every one of these is so exciting, and they include things like gravitational lensing and dark matter. And so Webb is just going to contribute to so many areas of science, and it's because it's got this incredible sensitivity in the infrared, it's got the resolution, and then it has these 4 incredible scientific instruments. Each one is unique, but is incredibly powerful. Some of them are more camera-based. Some of them can block light and do what's called a coronagraph to really look around some object that you block, like a star. Some of them have spectra. We actually have one that even has these little tiny shutters that are like the diameter of a human hair, and you can open individual shutters where there's galaxies, and then put that through something that spreads the light out. And for each galaxy, you get a spectra, so you can age them, as an example. So we have all these powerful instruments that are each going to do incredible things, and it'll be just a cornucopia of exploration.
I think that's incredible. So bottom line, I know we're getting there. I mean, you mentioned this a little bit. The mirrors are cooling. They're a few degrees above absolute zero, which is incredible. When does the science mission begin? What's the goal for that? When are we going to start seeing these images?
Well, the real question is, when is the first big release, right? And the plan was to do that 6 months after launch. So we launched on December 25th. And so I expect at the very end of June, the very beginning of July, you'll be hearing about some very big release, and I'm very optimistic. As you well know, we had these amazing deployments. The SunShield deployed, which was this incredibly complicated thing with all these membrane layers, and it went well. And the telescope deployed, the wings and the secondary, everything so far has gone incredibly well. The instruments are checking out well. We still have things to do. We're not there yet, especially on the telescope side. Until we have an image of a star that looks like a star, we can't say, yay, verily, we've built the right telescope, but we're on that path. And so that, that's where we're heading. So we're not quite there yet, but almost. I think we'll get there. And, and then there'll be after the telescope is aligned, there's about a 2-month period where the instruments are fully calibrated, and they take these they call them the early release observations. These are the ones that they're going to release, at the sort of beginning of July timeframe. And I think they're designed to really make an impact. I have no idea what they are. They keep that a secret. Even those of us working on it all these years don't know. Wow. And I kind of like it that way, because I'm looking forward to sharing the experience with all of your listeners.
Oh, well, we cannot wait. And Lee, if I had asked one last question, I know there's so much. I just think of the exoplanets and just everything that you're doing on there. Is there anything in particular that excites you the most as far as the results that you're looking forward to? Or is it everything?
Oh, wow. That's a great question because there's a lot of things. I mean, obviously the possibility that we could find chemical signatures that are unique to life.
Yeah.
There are scientists who study different molecules, and there are certain molecules that they believe only life would produce, and it turns out that by the way, infrared happens to be a great wavelength to look for molecules. I mean, things tend to have signatures where they absorb light, for example, in the infrared, and so the possibility of something like that. That would really be remarkable, but I also think just I remember the Eagle Nebula, on Hubble, when the Eagle Nebula came out, and I suspect there are going to be these equally incredible just pictures that are going to, give us this new view of the universe, and I don't know what they are. So part of it is like what I'm really excited about is just like to see things that we can't even imagine. And I think that's really cool. So.
Oh, I think it's going to be incredible. And Lee, I just want to congratulate you and the incredible team behind James Webb Space Telescope. I mean, it takes a village, it takes a lot of hard work.
Thousands of people all over the country, Europe, Canada also contributed, multiple companies all over the United States. And over 20 years, I've been fortunate to literally work with thousands of people. And I will tell you, they're the most dedicated, the most brilliant. You would be so incredibly proud of the United States, because the telescope is built completely within the United States, all over the United States, from Alabama to California to Ohio to New Jersey. And I will tell you, every one of these people are brilliant. They were dedicated. They all worked as a team. It's an amazing achievement that these people have done. So.
Well, thanks for inviting us along for the ride, because we're certainly on the edge of our seats, praising every moment that we see, every little accomplishment. We cannot wait for the actual images to come down. We're excited because, like you said, we don't know what to expect. So we're excited about that.
Exactly.
Lee, I just want to thank you so much for just all your hard work, and thanks so much for joining us today. Really appreciate it.
Yeah, no problem. Enjoyed talking with you, Chuck.
Thank you, Lee.
Your space journey.
Wow, I really enjoyed my conversation with Lee today, and I'm so excited, as I'm sure you are, about the James Webb Space Telescope. Exciting discoveries to be made. If you'd like to learn more, just go to NASA's website at web.nasa.gov. I want to thank Lee for joining me. I want to thank you for joining me as well. We'd also appreciate it if you'd share this episode with a friend. And if you're watching YouTube, if you can kindly give us a thumbs up, we'd appreciate that as well. Thank you so much for joining us. We'll see you next time. God bless.